And I believe it's recording. Fantastic. Okay, so I can introduce you now, Brent. So our speaker today is Brent Cody from Virginia Commonwealth University, and he is originally from CUNY, and we are very glad to have him back once again talking about higher indestructibility. Brent, go right ahead.
Oh yeah, and I just noticed there's a typo on the slide there. My email address is not at .com, it's at .edu. But yeah, so I'll talk about indescribability here. So this is some stuff I've been working on for the last 6 months or so, and the paper that I'm working on is almost done, but it hasn't been posted yet. But within a month, I probably will post this on the archive, so you can look for it there if you're interested. So I'll go over some of the background with indescribability, and then I'll talk about this idea of restricting formulas. I'll give you the definition of higher indescribability, and then we'll talk about some of its properties. We'll talk about universal formulas in this context, normal ideals, and some hierarchy results. And then if we have time at the end, I'll talk about generalization of construction by Bagaria, so something I call higher derived topologies. Okay, so first let's just talk about reflecting formulas. So this is something everybody knows really well, but if you have a normal ultra power embedding J, by the way, can you see my mouse on the screen? Yes, okay.
Yes.
So if you have a normal ultra power J and critical point kappa, so kappa is a measurable cardinal, then M and V agree on the power set of kappa. So if you take some first order formula that's true about kappa in V, then it remains true in M. And so M thinks that there's some alpha less than J of kappa where the formula is true. And then you can use elementarity to reflect that below kappa. So there's some alpha less than kappa where the formula is true in V. So the idea is to try to do this, but with formulas from infinitary logic. Let's consider the formula of phi sub zeta, where zeta is less than kappa, some ordinal less than kappa. This phi sub zeta is going to be the assertion that there exists an ordinal with at least zeta many predecessors. Okay, so there's some natural way to formulate this using infinitary logic, and I'll show you a little bit more of the details in a minute, but just for the moment, phi zeta is just the assertion there is an ordinal with at least zeta many predecessors. So then kappa thinks, from the perspective of V, kappa thinks that for every zeta less than kappa phi zeta, right? Kappa thinks that for every zeta less than kappa, there's an ordinal with zeta many predecessors. And then that remains true in M, right? Kappa still believes that infinitary formula. Okay, so M thinks that there's some alpha less than J of kappa where that formula is true. Okay, but of course we can't reflect the formula to some alpha less than kappa from this fact, right? Because it's just a contradiction, so you can't do that. However, you can reflect not the full formula, but you can reflect like a cut-off version of the formula, right? This is the idea. So even though you can't reflect this formula of length kappa, you can reflect the natural associated formula of length alpha, right? Alpha thinks that for every zeta less than alpha, there's some ordinal with zeta many predecessors. Okay, so that's kind of the simplistic idea associated to what I'm going to talk about here. Okay, so just a little background on indescribability. Everyone knows what pi1n formulas are. They have a n alternating second order quantifiers, beginning with a universal quantifier and ending with either a universal or a existential quantifier, depending on whether n is even or odd. And then psi is a pi10 formula. So that means the psi can have as many first order quantifiers as you want, and it can use second order parameters, and it can have second order variables in it. Right. So a set S is pi1n indescribable if whenever pi1n statement is true about V kappa, then there's some alpha in S where the formula is true at V alpha. Okay, so kappa is pi11 indescribable if and only if it's weakly compact, and there's many other basic facts you're probably familiar with. But, so Levy showed that there are universal pi1n formulas, and many nice properties of indescribable cardinals kind of fall out of this fact. So the existence of universal formulas is really powerful. So from that fact follows that pi1n indescribability is expressible by a pi1n plus 1 sentence. Okay, and then that yields a strict hierarchy corresponding to pi1n indescribability. So as n increases, you obtain hypotheses which are strictly larger in consistency strength. And also we have these associated normal ideals. So if kappa is a pi1n indescribable cardinal, then the set of subsets of kappa which are not pi1n indescribable, that's a normal ideal on kappa. A little more background. A set is pi10 indescribable in kappa if and only if kappa is inaccessible and S is stationary. So S intersects every club subset of kappa. And that's fairly easy just from the definitions. But and then now there's a generalization of that holds for the pi1n indescribable ideals. And this is due to Sun for n equals 1 and Helston for larger n. So if you assume kappa is pi1n indescribable, then a set is pi1n indescribable if and only if it intersects all pi1n clubs. Okay, so what is a pi1n club? Well, a pi10 club is just a club. A pi11 club is a stationary set which contains all of its inaccessible stationary reflection points. Okay, so it's a pi11 club is a stationary set that has a natural closure property that's weaker than clubness. Right? And then C is pi1n plus 1 club if it's pi1n indescribable in kappa, and for every alpha less than kappa, whenever C intersect alpha is pi1n indescribable, alpha has to be in C. Okay, and so if you take this as your definition of pi1n club, you can use it to characterize indescribable sets in a way that resembles the definition of stationarity. And for that reason, there's been kind of a lot of recent progress on taking theorems about stationarity and sort of transferring them to indescribability. Okay, so you can kind of view the stuff I'm talking about today as part of that larger idea. So I'm going to talk about pi1 Xi indescribability, where Xi can be any ordinal. And there are two main sources that I want to mention that from the literature where people have done this already. Sharp and Welch in 2011 defined a notion of pi1 Xi indescribability for transfinite Xi. Their definition is in terms of games. And their definition allows for a cardinal kappa to be pi1 Xi indescribable for all Xi less than kappa plus. And I don't want to say too much about this. Their definition does use canonical functions, which is something I'll talk about more. But really the stuff that I'm going to be talking about today is really more of an extension of a definition due to Bagaria in 2019. In his paper, Derived Topologies on Ordinals and Stationary Reflection. But in Bagaria's paper, he defines a notion of indescribability of kappa, which only works for Xi less than kappa. And I've been told that the two notions are equivalent for Xi less than kappa. However, as far as I'm concerned, that's still an open question, but I haven't been able to work out the details of that. Okay, so, and it certainly hasn't been published anywhere that these, the relationship between these two notions of indescribability. Okay, so what I want in this talk is a notion of pi1 Xi indescribability of kappa for Xi, which live between kappa and kappa plus, together with associated normal ideals, universal formulas, expressibility, and a hierarchy result. Okay, and just to be clear, these 4 bullet points here for these values of Xi are not covered at all by previous literature. Okay, so even for the Sharp-Welch definition, they only talk about it for cardinals, not for sets, so they don't have normal ideals. Brickhill and Welch in 2019 proved some things about universal formulas, but in this context of the Sharp-Welch indescribability, but only for xi less than kappa, not for xi greater than kappa. Okay, so there is, this thing that I want here is really something that isn't in the literature anymore. Okay, so let me talk about Bagaria's Pi1 xi indescribability first here. So first, let's define Pi1 xi formulas. So we talked about Pi1n formulas and sigma 1n formulas are similar. Okay, so hopefully those are familiar to you. So what are Pi1 omega formulas? Well, Pi1 omega formulas are just conjunctions. So a conjunction of a bunch of phi sub n's, where each phi sub n is Pi1n. Okay, so this is an infinitary formula, length omega, and each of the subformulas phi sub n is Pi1n. Sigma 1 omega formulas are similar. They're disjunctions of phi sub n's, where each phi sub n is sigma 1n. Okay, and then at successor steps in this construction, you just do the natural thing. So Pi1 omega plus 1 formulas are of the form, you have a universal second order quantifier followed by a psi, which is sigma 1 omega. Okay, and similarly for sigma 1 omega plus 1, you start with an existential second order quantifier followed by a Pi1 omega formula. Okay, and then in general, if xi is a limit, you just do this natural thing. Right, so once you see the sort of the omega step, you can guess how the rest of it's going to go. Right. Okay, so that defines Pi1 xi formulas, and now Bagaria defined that a set is Pi1 xi indescribable in kappa if and only if whenever a Pi1 xi statement is true about v kappa, there's some alpha in S where the statement reflects to v alpha. Okay. And he showed that, I think it's if kappa's omega Erdős, I think I had this on the slide earlier. If kappa's omega Erdős, then it's Pi1 xi indescribable for all xi less than kappa. But you can also easily see that if kappa is a measurable cardinal, then it's Pi1 xi indescribable for all xi less than kappa. And moreover, the set of alpha less than kappa that are Pi1 xi indescribable for all xi less than alpha is in any normal measure. But it's a standard reflection argument here. So essentially something we already went over. So if kappa is measurable and v kappa thinks that some Pi1 xi statement is true, where you're assuming xi is less than kappa, okay, then you can reflect it. So because p of v kappa is the same in M and B, v kappa thinks the same Pi1 xi statement is true. Okay, so M thinks that there's an alpha less than j of kappa where phi of j of a intersect v alpha is true. So you can reflect that to some phi alpha. Okay, but the thing I wanted to point out here is that this works because the length of phi is less than the critical point of j. Right. Okay, so what we want to talk about here is what if phi has lengths longer than the critical point of j? How can you still reflect things like that? Okay, so according to Bagaria, according to his definition here of indescribability, Pi1 xi indescribability, no cardinal kappa can be Pi1 kappa indescribable. Okay, so we're going to have to change the definition, but so let's understand why no cardinal kappa can be Pi1 kappa indescribable. Okay, so let's consider some statements here. So phi sub n of x, let's just let it be the statement that x is an ordinal with at least n predecessors. Okay, there's some natural first order statement that expresses that. Now, that's for each n less than omega. So phi sub omega is going to be the conjunction of phi sub n's for all n less than omega. Okay, and if you think about it, that phi sub omega is, what is it saying? It's saying that x is an ordinal, and for every n, x has at least n predecessors. So phi sub omega is equivalent to x is an ordinal at least as big as omega. Okay, and phi sub omega plus 1 of x is the assertion that there is some y smaller than x, which is an ordinal at least omega. So in other words, this is saying that x is an ordinal at least omega plus 1. Okay, and you can continue that up to kappa. So then what you get here, phi sub kappa, if you take the conjunction of all of those, that's a pi 1 kappa statement. And what it's saying is that X is an ordinal at least as big as kappa. So it's true about V kappa if you allow kappa as this second order predicate. So V kappa thinks phi sub kappa of kappa, but of course that formula doesn't reflect any smaller alpha, right? Okay, so what does reflect is some restricted version of the formula, right? So that's what we want to do. Okay, so in order to give you this definition of higher indescribability, we're going to use canonical functions. So let me just give you an example in case you're not familiar with this. An example for canonical functions. So you can use canonical functions to extend the Malo hierarchy in this way. Okay, so let's just recall kappa is 0 Malo if and only if it's inaccessible. For xi less than kappa, kappa is xi plus 1 Malo if and only if the set of alpha less than kappa that are xi Malo is stationary, right? So to define xi plus 1 Maloness, you just say that the set of alpha less than kappa of the previous degree is stationary, right? For limit xi less or equal kappa, you just say kappa is xi Malo if and only if it's zeta Malo for all zeta less than xi. Okay, but now when you get to kappa plus 1, you have to do something different, because when you get to kappa plus 1, you can say kappa is kappa plus 1 Malo. You want to say if and only if the set of alpha less than kappa is such that alpha is kappa Malo is stationary. But of course you can't say that because the distance from alpha to kappa is too big, right? So what you do is you diagonalize in a sense. So kappa is kappa plus 1 Malo if and only if the set of alpha less than kappa is such that alpha is alpha Malo is stationary. So in a sense, this degree of Maloness here, this alpha, is alpha's version of kappa, in a sense. Kappa is kappa plus 2 Malo if and only if the set of alpha less than kappa such that alpha is alpha plus 1 Malo is stationary. Okay, so this degree of Maloness, alpha plus 1, is alpha's version of kappa plus 1. Okay, so then when you get to arbitrary xi less than kappa plus, you can say kappa is xi plus 1 Malo if and only if the set of alpha less than kappa is such that alpha is f kappa xi of alpha Malo. Okay, so this f kappa xi, that's the xith canonical function. And you can think about f kappa xi of alpha as being alpha's version of xi. Okay, so this is kind of the way, if you're not familiar with canonical functions, this is kind of an easy way to see why they might be useful. Okay, so canonical functions are just these f kappa x's, and they, for any xi less than kappa plus, f kappa xi of alpha gives you a way to sort of talk about xi, but at alpha. Okay, so here's the definition of canonical functions, essentially. So for any regular kappa, there is a sequence of canonical functions, f kappa xi for xi less than kappa plus a kappa. And what this means is just that each of these functions is a function from kappa to kappa. The sequence of functions is increasing modulo the non-stationary ideal. So whenever zeta is less than xi, f kappa zeta is less than f kappa xi on a club. And the xth canonical function is canonical in the sense that it's sort of minimal. Okay, that's the second bullet point. So whenever you have a function f, which is greater than all f zetas for zeta less than xi on a club, then it's also greater than or equal to f kappa xi. So in a sense, what on a club. So in a sense, what that's saying is that f kappa xi is kind of minimal. Okay. So there's an easy way to show that these functions exist. You just have to verify that this definition works. So for xi less than kappa, you can take the xth canonical function to just be the constant function, xi. For xi equals kappa, the kappa canonical function, you can just take it to be the identity function. Okay, but now when xi is between kappa and kappa plus, to define f kappa xi, fix a bijection from kappa to xi, and then define the f kappa xi of alpha to be the order type of the image of alpha under that bijection. Okay, and that's always going to give you something less than alpha plus. So what it's doing is you're taking C, which lived between kappa and kappa plus, and this function f kappa c spits something out that's less than alpha plus. So this thing is sort of like alpha's version of C. Okay, and you can just verify easily that this definition satisfies these properties. The Cth canonical function is independent of which bijection you use, b kappa c, modulo the non-stationary ideal. So in other words, if you had chosen some other bijection, b kappa c prime, then the set of alpha where these two definitions agree contains a club. So in that sense, the Cth canonical function is kind of well-defined. Right, I said this, for xi less than kappa plus, think of f kappa xi of alpha as alpha's version of xi. Another useful thing about these canonical functions is that they represent, the Cth canonical function represents xi in any normal ultra power. So j of f xi of kappa equals xi. Okay. Okay, so let's go back to our question. Can we reflect long formulas in the way that I was talking about? So what would you want to have happen? So let's fix a normal ultra power embedding with critical point kappa. And let's assume v kappa satisfies some pi win xi formula. Okay, so this is a formula of length xi where each phi zeta is pi win zeta. So what you want, we want to define some notion of restriction of formulas so that there's some alpha less than kappa where a restricted version of the full formula is satisfied by v alpha. Okay, and what you can think about this restricted version of the full formula as being sort of alpha's version of the full formula. Okay, and so it's tempting to sort of take the long formula, the full formula, and define the restriction to alpha by just cutting the formula off using the Cth canonical function evaluated at alpha. Okay, but there's a problem with that. That doesn't work. And the reason is essentially because of ghost coordinates in the normal ultra power embedding. So if you apply j to this pi 1 xi formula, this is a long formula. It has lengths longer than the critical point. So when you apply j to that formula, it stretches the formula, right? So you're going to get a longer formula. Now, when you look at the first kappa many subformulas, you can understand those as just being j of the individual subformulas in the original formula, okay? But starting at kappa, you have ghost coordinates, right? So in this section of the formula, you'll have ghost coordinates. For example, between kappa and j of kappa, you have these mysterious phi bar zetas, and you can't really get a handle on them. And for that reason, this simple definition of restriction there doesn't work. You can't make the reflection argument work, at least with a measurability embedding. Okay, so what you want, in order to make the reflection argument work, what you want is this formula, that when you apply j to a long formula, it gets stretched. And what you want to have happen is that when you restrict that stretched formula to kappa, you want to end up with the original formula. Okay. All right, so how can we do this? So we need to somehow come up with a definition that deals with ghost coordinates in a way to avoid this problem. Okay, so we're going to define a related sequence of functions. This is a sequence related to the canonical functions. So fix a sequence of bijections for each xi between kappa and kappa plus. Fix a bijection b kappa xi from kappa to xi, and then define the corresponding sequence of canonical reflection functions at kappa as follows. So each of these functions is not going to be a function from kappa to kappa, but rather these functions are going to take values in p kappa kappa plus. For xi less than kappa, you just make f kappa xi the constant function xi. But then when you get to xi starting at kappa and below kappa plus, f kappa xi of alpha is just going to be defined to be the image under the bijection of alpha. Okay, so the only difference between these functions and the canonical functions is that we didn't take the order type here. right? If we put order type here, that's just the definition of canonical functions. So you can think of these f kappa xc's as being non-transitive versions of the canonical function. So in other words, f kappa xc of alpha is like a non-transitive version of f kappa xc of alpha, right? The uppercase one is a non-transitive version of the lowercase one. So for example, if you take the transitive collapse of f kappa xc of alpha, the capital one, then you get the lowercase one. Okay. So let me just, there are some pictures here to maybe help understand what's going on. So at the top here, we just have pictures of the bijections. So the b kappa kappa bijection is just the identity function. It's a bijection from kappa to kappa. B kappa kappa plus 1 is a bijection from kappa to kappa plus 1. And so it doesn't matter how which particular bijection you take, it doesn't matter, but at least for the small values of xc, there's usually a natural way of doing it. So for example, here we map 0 to kappa, and then we map 1 to 0, 2 to 1, and so on. So eventually this bijection is going to be the identity function. Okay, and as long as xc is relatively small, so if xc is less than kappa plus kappa, you can take b kappa xc to just map an initial segment of kappa to the interval from kappa to xc, and then map the remainder of kappa in a bijective way to all of kappa, okay? Now that there's a kind of a conceptual change when you get to xc equals kappa plus kappa, because now you have kappa much stuff above kappa and kappa much stuff below kappa, but you just map the evens to kappa and map the odds above kappa. Okay, you can make this work out, right? Okay, so these are the bijections. So now what is, how should you visualize these canonical reflection functions? So in this picture, this dotted line represents the bijection from kappa to xc. And if you want to know what the xth canonical reflection function looks like when you apply it to alpha, it's going to look like this. So for club many alpha, f kappa xc of alpha is just going to be a copy, it's going to be alpha together with some extra stuff above kappa. Okay, and that's an element of p kappa kappa plus. Right. Okay, so so here's just the first few canonical reflection functions. F kappa kappa, capital F kappa kappa is just the identity. F kappa kappa plus 1, at least for club many alpha, is just going to be alpha union singleton kappa. F kappa kappa plus 2 is alpha union kappa comma kappa plus 1, and so on. F kappa kappa plus omega is this, and notice that F kappa kappa plus omega of alpha is the union of it's just the union of the previous ones, right? F kappa kappa plus kappa of alpha is alpha, this should be union here, union with the interval from kappa to kappa plus alpha. Okay, so notice, like, if you take the transitive collapse of any of these, it's going to output the value of the corresponding canonical function. Okay, and just like with canonical functions, the definitions here don't depend on which bijections you use, at least modulo the non-stationary ideal. Okay, so one nice fact about these canonical reflection functions is that, let's see, the canonical functions represented ordinals in normal ultrapowers, but these canonical reflection functions represent something else. So if you take a normal ultrapower embedding, the xth canonical reflection function represents J image xc in the ultrapower. Okay, and this is for all xc less than kappa plus. Okay. Okay, so now these canonical reflection functions satisfy some properties analogous to canonical functions. So for example, the sequence of functions is increasing modulo the non-stationary ideal. So as long as zeta is less than xc, f kappa zeta is going to be strictly contained in f kappa xc on a club. At limits xc, the value of the xth canonical function is determined by the union of the previous ones, at least on a club. And then you have a kind of minimality property for the xth canonical function, but only when xc is a limit. This is kind of strange. I mean, I think this is basically due to the fact that the ordering on p kappa kappa plus is subset rather than less than. So it's not a well-founded ordering, but nonetheless, you can show that if Xi is a limit ordinal, then the Xth canonical reflection function is in fact canonical in the sense that it's minimal. So if you have any other function f from kappa to p kappa kappa plus, which has the property that this is backwards. This should say it has the property that for all zeta less than Xi, f kappa zeta is contained in f of alpha. Then yeah, there's a typo here, but hopefully you understand what I'm saying. So I want to express some minimality property here. Right, so you want to say that whenever f is a function which is above all the f kappa zetas on a club, then it's also above f kappa Xi, right? So I should have just changed this to f. Yeah. Okay. So I believe these canonical reflection functions are sort of folklore, but I haven't found them anywhere in literature. I mean, I think they're kind of like, they're used to prove results about canonical functions, but I haven't found those proofs anywhere. So, but they satisfy many nice properties. So here's one really nice coherence property. And some of these properties, for example, for canonical reflection functions, don't have analogs for the canonical functions. But what this is saying is that for let's see, yeah, if Xi is a limit ordinal less than kappa plus, then for club mini alpha, whenever you take any zeta, which is an element of f kappa Xi of alpha, and then you restrict f kappa Xi of alpha to zeta, then you just get f kappa zeta of alpha. Okay, so this is kind of a natural coherence property. And there's a long list of properties like this that are at work behind the scenes in a lot of the things I'm going to be showing you. Okay. Okay, so here's a definition of restriction of formulas that is going to work to do what we want. So we're going to define restriction of pi 1 Xi and sigma 1 Xi formulas by induction on Xi less than kappa plus. Okay, so for pi 1 0 and sigma 1 0 formulas, they look like this. They just have some number of free variables, some number of second order parameters, and they have some first order quantifiers, okay, but no second order quantifiers. And so we're just going to define the restriction of such a formula to be just the formula, except you cut down the second order parameters to alpha. Okay, and if Xi is a limit, then what you're looking at is phi is a long conjunction. And what we're going to do is, and this is a pi 1 Xi formula over v kappa, and what we're going to do when we restrict it to alpha is we're going to cut the formula down by restricting which indices we use. Now the length of this formula is going to be given by the canonical function f kappa Xi, okay, but the indices that we look at are given by the canonical reflection function. Okay, so we're not just taking an initial segment, right? Our restriction is going to have sort of holes in it. The set of indices is going to have holes in it. And then you do a similar thing for sigma 1 Xi. And inductively, then you restrict the subformulas too. And then at successors, it's easier. You don't do anything to the quantifier. You just restrict the subformula. Okay, so that's sort of the main definition. Okay, so one thing to notice is that this computation of these restrictions does depend on which sequence of canonical reflection functions you use, right? It does depend on that. But modulo the non-stationary ideal, it doesn't depend on which sequence of canonical functions you choose, right? And also notice that if phi of A is pi 1 Xi over v kappa, where Xi is less than kappa, then when you restrict phi of A, you're just getting phi with the parameter cut down. You're essentially not doing anything extra. Okay, so this is kind of only relevant for Xi between kappa and kappa plus. Okay, and so here's the definition. So if kappa is a cardinal, Xi is less than kappa plus. A subset of kappa is pi 1 Xi indescribable if and only if whenever a pi 1 Xi sentence is true about V kappa, there's some alpha in S where the restriction of that formula is true about V alpha. Okay, this definition agrees with Bagaria's definition for Xi less than kappa. And also this definition of indescribability here is actually fully independent of which sequence of canonical reflection functions we choose. So even though the definition of the restriction of these formulas is only independent of our choices modulo the non-stationary ideal, when you make this definition of indescribability, it doesn't matter which sequence of functions you choose to compute these restrictions with respect to. Okay, so if kappa is measurable, then kappa is pi 1 Xi indescribable for all Xi less than kappa plus, and moreover, the alpha is less than kappa, where alpha is pi 1 zeta indescribable for all zeta less than alpha plus is measure 1. Okay, so let's talk about that. This is not hard, but let's just see how it works. So let's let J be normal ultra power embedding. And what we're going to do first is we're going to argue by induction that for induction on Xi less than kappa plus, that whenever phi is a pi 1 Xi formula over V kappa, if you take J of that formula and restrict it to kappa, then you just get the original formula back. So fix Xi less than kappa plus. Let's assume that Xi is a limit ordinal for the purposes of this. So that means phi is one of these big long conjunctions. And it's pi 1 Xi, so the subformulas phi zeta are pi 1 zeta. And we're going to assume that this result here holds for these phi sub zetas. So when you take J of that formula, it's going to get stretched, right? So if you apply J to the sequence of subformulas, it's going to be a sequence of length J of Xi. And similarly, if we apply J to the sequence of canonical reflection functions, you're going to get a sequence of length J of kappa. So that sequence gets stretched too. And then by elementarity, these F bar functions are canonical reflection functions at J of kappa in M. Okay, so what happens when we take J of phi and restrict it to kappa? So J of phi will be this stretched formula. Okay, and when we restrict it to kappa, what we're going to do is use the J of Xith canonical reflection function at J of kappa to limit which indices we're looking at. So we just take the conjunction over those zetas that live in this set. And then we restrict the subformulas. That's just the definition of restriction. Okay, but this is the J of Xith canonical reflection function at J of kappa. So it's also equal to J of the Xith canonical reflection function at kappa, right? So we can change the index set to J of F Xi of kappa. Okay, but we saw already J of F Xi of kappa represents J image Xi in the normal ultra power. So we're really just taking our conjunction over J image Xi. Okay, so now that means that for each zeta in our index set, each zeta is of the form J of eta, right? So, but phi bar J of eta is J of phi eta. So this means that we're really looking at the conjunction over zeta less than Xi of J of phi zeta restricted to kappa. Okay, but now by induction, when you restrict J of phi zeta to kappa, you just get phi zeta. Right? Okay, so when you apply J to a pi 1 Xi statement, and then you restrict it to kappa, you just get the same statement back. Okay, so that's going to make the reflection argument work. So if we assume V kappa satisfies some pi 1 Xi statement over V kappa, then the same statement is satisfied in M at V kappa. So M thinks that there's some alpha less than J of kappa such that V alpha satisfies J of phi restricted to alpha. Okay, by elementarity, there's an alpha less than kappa where V alpha satisfies the restriction of phi. Okay, and this so I only did part of the statement of this result, but the rest of it is similar. Okay, so hopefully at least now you believe that this pi1 Xi indescribability for Xi greater than kappa is at least consistent relative to a measurable cardinal. Okay, so let's talk about universal formulas now.
Can I ask a question?
Yeah, sure.
So measurable is an upper bound. Do you know if it's equiconsistent or?
These. So okay, so if kappa is Ramsey, yeah, what do I want to say? So okay, so a kappa which is pi1 Xi indescribable for all Xi less than kappa plus is strictly weaker than a Ramsey. I know that.
Okay, so it is weaker than
a measurable, yeah.
Okay, so and even weaker than a measurable.
Yeah, it's strictly weaker than a Ramsey, in fact. But
how do you make the argument?
I mean, it's essentially similar to this. Yeah, so for those Ramsey embeddings, you have the same power set of kappa, right? And that's more or less what it comes down to.
I see.
Yeah.
Okay.
Yeah.
Thanks, Brent.
Any other questions? But so I don't know if it's weaker than a Ramsey. So yeah, that's a good question. Bagaria got his hypothesis down to omega Erdős, but I don't know if that can be done for these. Okay, so universal formulas. So Levy proved that universal pi1n formulas exist. So what does that mean? So for every n less than omega, there is a pi1n formula. Call it psi n of xk. So x is a second order variable, k is a first order variable. They're universal in the sense that if you take any other pi1n formula, phi of x, then there's some code for that formula, k phi less than omega, such that for all second order parameters a and all sufficiently closed alpha less or equal kappa, the truth of phi about the alpha is equivalent to the truth of the universal formula evaluated at the code of phi. Right, so there's one formula that can be used to test the truth of all pi1n formulas if you just feed in the correct code. And Levy used Gödel coding to get universal pi10 formula. That's kind of at the time, even that was kind of a standard thing. And then inductively, you can prove once you have a universal pi10 formula, it's not too hard to prove that you have universal pi1n formulas for all n. Okay, and then Bagaria did a similar thing for Xi less than kappa. So for regular kappa, Xi less than kappa, universal pi1 Xi formula exists. This means there's some pi1 Xi formula, looks the same as Levy's, such that for all pi1 Xi formulas phi, there's a code. Okay, but notice this time the code is not a natural number, but this time the code is a subset of Xi. Such that for all second order parameters and all alpha, which are sufficiently closed, but also notice this alpha has to be bigger than C. You have that the arbitrarily chosen formula phi is true about the alpha if and only if the universal formula is true if you feed in the code for phi. Right, and Bagaria's proof starts the same way as Levy's does, and then continue inductively. And really, you just have to worry about limit steps here. The successor steps are similar to Levy's proof. But if you think about what you have to do at limit steps, for example, at limit steps, you have a pi1 Xi formula, an arbitrarily chosen pi1 Xi formula, and you want a universal formula that's going to tell you when this formula is true. So you want a code for this formula. So what is the code going to be? Well, inductively, you have codes for all the subformulas, phi zeta. So you have essentially a Xi sequence of codes. And so the code for phi is just going to be some subset of xi which codes the sequence of codes for previous formulas, right? And then the universal pi1 xi formula is essentially just a conjunction of all the previously defined universal formulas, okay? Except for you just have to make sure that you are using the right code in the right place. So this notation just kind of makes sure that you're extracting the correct slice of the code in the right place. Okay. Okay, so what about for xi greater than kappa? So here's the definition of universal formula in that context. So if xi is between kappa and kappa plus, a formula psi of xk is a universal pi1 xi formula at kappa if for all pi1 xi formulas phi, there's a code. Okay, but now notice this code is a second order parameter, right? This code is a subset of kappa. And there's a club, C phi, such that for all parameters A, I guess this should be a subset of V kappa, and all alpha in the club, or equal to kappa, you have that the formula, the restriction of that formula holds at V alpha, if and only if the restriction of the universal formula holds at alpha. Okay. Now, when alpha equals kappa, and you restrict from kappa to kappa, it just doesn't do anything. That's just, it doesn't change the formula at all. Okay, so this is what I mean by universal pi1 xi formula in this context. Okay, there's some added complexity here because you have to restrict things, but. Okay, so these, in this context, universal formulas do exist. So for any xi between kappa and kappa plus, as long as kappa is regular and uncountable, there's a universal pi1 xi formula. And also a universal sigma 1 xi formula. Okay, so what's the idea? The idea is kind of similar to what was done previously, but slightly more complication. So fix a limit ordinal xi between kappa and kappa plus. So think about what a code for an arbitrary pi1 xi formula is going to have to be. Inductively, you have codes for each phi zeta. That's the sequence k phi zeta. Okay, and you want the code for phi to somehow code all the previous codes. So you need to code the sequence, but xi is bigger than kappa. So to do that, you're gonna need k phi to be a subset of kappa. Right? So this code for this formula is going to be a second order parameter. So how do you take a sequence of length xi and code it into a subset of kappa? Well, you can use a fixed bijection from kappa to xi to sort of re-index that sequence so it becomes a kappa sequence, and then just use some kind of standard pairing to get a single subset of kappa. But then when you write down the universal formula, you just need to make sure that, again, like at the zetith index, you're using the correct slice of your code. Okay, so this can all be worked out. And also, like, remember, you have these various clubs that work for each zeta. So each zeta comes along with a club. Okay, each subformula phi zeta comes along with a club on which the universal formula for phi zeta works. So at xi, you just take the diagonal intersection of the xi many clubs, and that gives you a club where this universal formula is going to work. Okay. Okay, so once you have universal formulas, it's fairly straightforward to show that there are normal ideals associated with pi1 xi indescribability for xi less than kappa plus. Yeah, okay. We'll come back and use this a little bit later, but so now, once you have these normal ideals, the next task is to try to show that these hypotheses are actually increasing in consistency strength, so strictly increasing. And so to do that, you want to show that pi1 xi indescribability is actually expressible by a pi1 xi plus 1 formula in the same way that pi1 n indescribability is expressible by a pi1 n plus 1 formula. Okay, but up to this point, like the universal formulas and the normal ideal stuff, these two results were, it's not that they were easy, but they were relatively straightforward. But what I found when I got here was a bunch of things come up that just don't exist in the previous arguments. So let's talk about some of that. So to do this, to establish this hierarchy results, we're going to need a bunch of lemmas, and there are some here that I'm not even going to talk about here. But so there's a long sequence of lemmas that leads up to this result. But okay, so this lemma, what is it saying? So if you fix n xc less than kappa plus, and you let psi kappa xc be the universal pi 1 xc formula at kappa that we just defined, then there's a club such that for all regular alpha in the club, when you restrict that universal formula to alpha, you get a pi 1 f kappa xc of alpha universal formula at alpha. Okay, so one thing to point out here before we go on is this, this definition that I sketched for you here isn't really unique. It's not like there is a single universal pi 1 xc formula, but there will be many, many universal pi 1 xc formulas, right? Because each bijection that allows you to sort of code these codes into a single set could be used here to get a universal formula too, right? So there are going to be many universal formulas that fall out of this definition, and the point here is that if you take a universal formula, universal pi 1 xc formula at kappa, and you restrict it to alpha, often you're going to get some universal pi 1 f kappa xc of alpha formula. Okay, and this index here, the f kappa xc of alpha, should make sense because psi kappa xc was a pi 1 xc formula. So when you restrict it to alpha, you're looking at sort of alpha's version of that formula. So it should make sense that it's pi 1 f kappa xc of alpha over v alpha. Okay. Another thing, this is another thing that kind of came up that sort of has an analog in the canonical function context, but what this lemma is saying is that there's a connection between the canonical reflection functions at kappa and the canonical reflection functions at alpha, where alpha is less than kappa. Okay, no matter how you choose your bijections. Okay, so what is that connection? So fix xc less than kappa. For each alpha less than kappa, let pi xc alpha denote the transitive collapse that we talked about. Then there's a club in kappa such that for all regular members of that club, the alpha, there are club many beta less than alpha, where if you take the transitive collapse of f kappa xc of alpha and you compute the image of f kappa xc of beta, so beta is less than alpha, then what you get is f alpha f kappa xc of alpha of beta. Okay, so it's telling you there's a connection between, no matter how you choose your bijections, there's a connection between the canonical reflection functions at kappa and the canonical reflection functions at alpha. Okay, and you can, this is a little hard to understand at first, but here's a picture that might help. So I want to try to explain this equation that's in that lemma. So here's a bijection from kappa to xc. Right? We use this bijection to compute f kappa xc of alpha and f kappa xc of beta. And what this lemma is saying is that for club many alpha, if you look at f kappa xc of alpha, that's the shaded portion right in the middle there. Okay, then for club many beta in alpha, if you apply the transitive collapse pi xc alpha of f kappa xc alpha, but you apply it to this subset of f kappa xc alpha, you apply it to f kappa xc beta, then what you end up with is this set over here. And what the lemma is saying is that that set can also be obtained in another way. Okay, it can be obtained by using the bijection at alpha from alpha to f kappa xc of alpha and taking the image under that bijection of beta. Okay, so this is kind of a complicated coherence property that holds no matter how you choose your bijections. Okay, but it's not saying it happens all the time, but it happens often, right? Like club often, this happens. So one consequence of that is this theorem. I call this a theorem, even though it's a little bit technical, because I ended up needing this theorem in many, many places, not just in the way I'm describing here. But so what this is telling you is, if you have a pi-wing-c formula, then there's a club in kappa such that for all regular alpha in the club, there are club many beta, such that if you take phi and you restrict it to alpha, and then you restrict it from alpha to beta, that's the same as just restricting phi to beta. Okay, so in other words, beta's version of phi, okay, that's the right-hand side, beta's version of phi is the same as alpha's version of phi restricted to beta. Right? And again, that doesn't happen all the time, but it happens club often. Right? Okay, so if you put those three results that I just discussed together, so the fact that when you restrict universal formulas, you get universal formulas, club often. You have this sort of complicated coherence property, and then this double restriction property. When you put those together, you get this, okay, which is a expressibility result. So there is a pi-wing-c plus 1 formula over v kappa in a club in kappa such that for every subset of kappa, S is pi-wing-c indescribable as a subset of kappa if and only if this formula holds at v kappa about S. Okay, so in other words, this formula characterizes when a set is pi-wing-c indescribable in kappa. Moreover, club often, when you restrict the formula to some alpha, that restriction characterizes when a set is pi1 f kappa c of alpha indescribable in alpha. Okay. Yeah. Okay. So I won't say much more about that, but this is an expressibility result that is analogous to the classical one. Okay. So you can now use that expressibility to get a hierarchy result. So if S is any pi1c indescribable set where xc is less than kappa plus and zeta is less than xc, then the set of alpha where S intersect alpha is pi1 f kappa zeta of alpha indescribable is in the pi1c filter. Okay, so I won't say very much about this, but let's just think about the example. So this is a special case of the corollary. So if kappa is kappa plus 2 indescribable, then there are many alpha less than kappa that are alpha plus 1 indescribable. All right, so this is a hierarchy result. Okay. And so another thing this shows is that these ideals are strictly increasing. So you're getting new information from the ideals. So if kappa is pi-wing-c indescribable for some c less than kappa plus, then for any zeta less than c, the pi-1 zeta ideal is strictly contained in the pi-wing-c ideal. And you can show this as follows. So the set of alpha less than kappa where alpha is not pi1 f kappa zeta of alpha indescribable is measure 0 with respect to the pi1c ideal, but it's positive with respect to the pi1 zeta ideal. Okay. I also wanted to talk about another characterization of indescribability. Although, let's see, how much more do I want to do? Maybe I'll skip this club stuff, but the point of this stuff was that you can characterize this higher indescribability in terms of a natural filter base in the same way, so that it resembles the definition of stationarity. And that's bullet point 1 here. The set is pi-wing-c indescribable if and only if it intersects all pi-wing-c clubs. Okay.
If you want to talk for like another 15 minutes, Brent, it's perfectly fine. So.
Oh, okay.
It's up to you.
Okay. Well. Okay, so let me just briefly talk about these definitions then. So this is the definition of pi1c club. Okay, this is going to work to do the result I just mentioned. So pi10 clubs are just closed unbounded sets. Pi1 zeta plus 1 clubs are pi1 zeta indescribable sets, which have a closure property. So in other words, for club many alpha, if C intersect alpha is indescribable enough, so if it's pi1 f kappa zeta of alpha indescribable, then you have to have alpha in C. This is a closure property of C, kind of like the pi1n clubs that we talked about at the beginning. And then you can also do a similar thing at limits. So at limits, C is a pi1 zeta club if it's pi1 zeta indescribable for all zeta less than C. And there's a club of alphas where whenever C intersect alpha is pi1 zeta indescribable for all zeta less than f kappa C of alpha, then you have to have alpha in C. Okay, and this all agrees with the pi1n club definition, and it extends naturally to this context. Okay, so maybe, yeah, so I think in 5 more minutes I can talk about this application. So in Bagaria's 2019 paper, he defined a natural sequence of topologies, and these are coming out of a larger context, something about modal logic. I think Andreas has done some work on things related to this, but I'm not going to get too much into the background of that, but I just wanted to describe an application of higher indescribability. So let's go over Bagaria's results first. So he defined the sequence of topologies on any ordinal mu, okay, in the following way. Tau 0 is just the interval topology on mu, okay, it has base B0. And then to define T1, you take the Cantor derivative operator from power set of mu to power set of mu. And if you're given tau xi, you're going to define this d xi as just take d xi of A is going to be the set of limit points of A under the t xi, tau xi topology. And then tau xi plus 1 is the topology generated by the previous basis together with the set of all d xi of A's. So you're basically, so for example, at T1, you're taking as your basis intervals, but then you're also throwing in any set, which is the set of limit points of the set. Okay, now those sets are going to be considered open in tau 1, right? And then you can just continue. So at limits, you just take the union of the previous bases, and that generates a topology, and you can continue this, right? So there's some interesting results about this. So basically, one question is like, are these topologies even non-trivial? I mean, maybe at some point you're just going to get every set is open, right? So you're going to get the discrete topology. But Bagaria showed that a point alpha less than mu is non-isolated in, say, tau 2, if and only if simultaneous stationary reflection holds at alpha. And that meaning that every pair of stationary subsets of alpha has a common stationary reflection point. Okay, so at least if mu has the property that simultaneous stationary reflection property, the simultaneous stationary reflection holds at some alpha less than mu, then tau 2 is going to be non-trivial on mu, right? He also gave a characterization of when the point is non-isolated for larger tau x's. Okay, and it's a generalization of that first bullet point there. So for all xi, an ordinal alpha less than mu is non-isolated in the tau xi topology, if and only if alpha is xi simultaneous reflecting. Okay, so this just means, this is a generalization of simultaneous stationary reflection. So let me leave it vague like that, but I can show you the definition of xi s reflecting in a second if you want. But for xi less than kappa, he also showed that if alpha is less than mu is pi1 xi indescribable, then in particular it's also xi plus 1 s reflecting. So from pi1 xi indescribable cardinals, you can get the non-triviality of these derived topologies. Because if some alpha less than mu is pi1 xi indescribable, then it's xi plus 1 s reflecting, and therefore it's a non-isolated point in the topology. And then in fact, he proved that in L, pi1 Xi indescribability is equivalent to Xi plus 1s reflecting, okay? And this can be viewed as a generalization of Jensen's result that in L, weak compactness is equivalent to simultaneous stationary reflection. Or sorry, it's just equivalent to stationary reflection. Okay, but in Bagaria's definitions, no alpha can be alpha plus 1s reflecting, okay? And this, you can think of this as being kind of analogous to the fact that under Bagaria's definitions, no kappa can be pi1 kappa indescribable. So what this means is that Bagaria obtains the non-discreteness for these tau Xi topologies on mu for all Xi less than mu. Okay, and then the idea here is to try to push this beyond Xi less than mu, right? So what we can do is define a sequence of topologies tau Xi for Xi less than mu plus that are going to agree with Bagaria's topologies for Xi less than mu. Okay, so for tau 0, you just use the interval topology. Now, what we're going to do is change the definition of the Cantor derivative operator. So this is kind of like a diagonal version of the Cantor derivative operator. So given a topology tau Xi on mu, d Xi of A, this is a typo, this should be d Xi. D Xi of A is going to be the set of all alpha less than mu, where alpha is a limit point of A in the tau sub f mu Xi of alpha topology. Okay, so this is like a diagonal Cantor derivative where you're sort of, you're changing which topologies you're looking at when you calculate limit points, okay, of a given set. Okay, and this definition, it's easy to see that it agrees with Bagaria's definition for Xi less than mu, because for Xi less than mu, f mu Xi is just the constant function Xi, right? So this would just be tau Xi for Xi less than mu. And then you just continue the definition. So tau Xi plus 1 is the topology generated by the previous basis, and then the set of these new sets of limit points. And at limits, you take unions. Okay, so this kind of defines a sequence of topologies, tau Xi for Xi less than mu plus. And then you can generalize, at least I've been able to generalize some of Bagaria's results, not the result about L, but some of these other ones. So for example, for all Xi less than mu plus, there's a club in mu such that for all alpha in C, alpha is non-isolated in this tau Xi topology, if and only if alpha is f mu Xi of alpha s reflecting. Okay, so I had to change the definition of reflecting because notice, like f mu Xi of alpha will quite likely be larger than alpha. And under Bagaria's definition, alpha cannot be alpha plus 1 s reflecting. Okay, so that required a change too. But and then if a cardinal kappa is pi1 Xi indescribable for some Xi less than kappa plus, then it's also Xi plus 1 s reflecting. Okay, so both of those results, when you change, when you look at these results for Xi less than kappa, they just become Bagaria's results. Okay, but this is an extension of them to Xi bigger than mu. Okay, I think I'll stop there. If you want to see the definitions of these Xi stationary things, I can show that, but I'll stop there unless there are any questions.
All right, everyone, let's thank Brent for a really nice talk. I just do the clapping icon. As terrible as it is, there's just no way to clap on Zoom. Questions for Brent?
Okay, I have a question from way back in the beginning, definition of pi1 Xi formulas.
Okay.
So at successive stages, you put on some additional quantifiers the way you do with pi1n. And then at limit stages, you take unitary conjunctions or disjunctions. So what I'm thinking, sort of a two-dimensional picture in mind where you have more in that direction, more conjunctions and disjunctions in that direction. And the hierarchy goes sort of zigzagging, going that way at successors and up at limits and so on. Is there anything in the rest of the plane besides just that particular path going through? Is there anything
Huh.
interesting to the plane? Maybe I should say.
I'm not sure I understand the question.
Okay.
So
Suppose instead of saying successors at successors add a quantifier, at limits
yeah,
do a conjunction.
yeah.
Suppose I just picked the point in the plane and said, okay, let's just go up there any way that makes sense. Maybe do a lot of conjunctions first and disjunctions nested, and then
Oh, I
add
see.
quantifiers, or just, there's lots of room in the plane.
Yeah.
Do you get to anything interesting, or is it all going to agree on a club with what you had anyway?
I think I see what you're saying. I'm not quite sure. So your example, so for example, you could consider formulas which are very long conjunctions, but where all the subformulas are only pi1n.
Yeah, so
Yeah,
high up and
I see
near
what
the
you're saying.
edge.
Yeah, that's a really good question. I don't know the answer. Thanks.
Okay.
Anyone else? Okay, so I have a question going back to the hierarchy of the large cardinal notions that you get out of this. So let me see if I understand it right. So the entire hierarchy is below a Ramsey cardinal?
Yeah.
Definitely below, right? Not that Ramsey is a limit of pi1c.
Yeah.
Okay. And so the pi1n's, I think, are very low in the hierarchy. They are below a subtle cardinal. Is this correct? I don't.
Yeah.
Okay, so can you play some of the other interesting ones somewhere within the known large cardinal hierarchy? Do you know?
Are you asking if I can put a better upper bound on?
So omega Erdos, you said, is above the pi1c for xc less than kappa, right?
Yeah.
Okay. Are there any other interesting correspondences? Like, what do we know about indescribability of say, an ineffable cardinal, or any of the sort of known large cardinals?
Oh, yeah.
Terms of these higher indescribability.
Okay. Actually, this is one reason that I started looking at this, was that the stuff that I talked about at CUNY a while back with the Ramsey hierarchy and a refinement of the Ramsey hierarchy using indescribability. The motivation for looking at this was to continue that analysis of the Ramsey hierarchy above kappa Ramsey. Right. But I don't know what to say about that yet. I haven't looked at it yet. But I think, so for example, if kappa is Ramsey, then it's pi1 indescribable. If kappa is ineffable, then it's pi1 indescribable. And then as you work your way up the ineffability hierarchy and the Ramsey hierarchy, the degrees of indescribability that you can withdraw increase. Yeah. And so there should be some results about this higher indescribability in relationship to the higher levels of the ineffability and Ramsey hierarchies. But I haven't done that yet. Yeah, okay, that's actually like probably what I'll be working on in a few months.
I see.
Yeah.
All right, anyone else? Last chance. Any questions? All right, in that case, thanks very much again, Brent. This was super interesting. Next week we have Gunther speaking, so he is now in charge of Zoom. I am only host, thankfully, for this week. This was stressful. I do not want to do it again. And I have his title and abstract up on the website already. So I think that's it for the, so this Zoom, the Zoom link that we're using now, we will be using for the foreseeable future. I will keep repeating it in the emails, but it will be the same Zoom link. And if you're not on my mailing list and you want to get on my mailing list, please let me know. I send an email generally only once a week, 1 hour before the seminar as a reminder. All right, I think that is now definitely it for the announcement. So I will see you all next week, hopefully.
Okay, thanks for listening, everybody.
Thanks for the talk, Brent.
Yeah, no problem.
Thank you, Brent.
Yes, thank you, Brent. Very interesting.
No problem, yeah.